So the specific internal energy U of a pure substance in a thermodynamic equilibrium is a function. So U in a pure substance at thermodynamic equilibrium is a function only of the states of substance, which is a state of substance, and it is a property of the substance. So what we already established regarding on the property of substance even before we establish the first law, a property of substance is P, V, and T. So when we goes to the conservation of energy in the first law, in the derivation of the first law, we obtain another property of the substance or state properties, and then even before we go to the first law as well, when we are looking at the properties of the substance PVT here, we already have a state. We already have a state equation. So if we're dealing with the ideal gas equation, so P V equal to RT, which means that P can be a function of VRT, V can be a function of PRT, or T can be a function of PV. So when we're dealing with this kind of thing, we are looking through a surface diagram that describes this equation of states, such a way that we could build up a surface where I have volume P, and temperature, such a way that and then from this surface we notice that the state is only possible within this surface. It cannot be possible, and so it's consistent to the condition that if I were to state a pressure and a temperature of a system, and then from this surface diagram I directly get the volume of that system. So I can only limit to select the state properties, the value of the state properties of the two state parameters, and then the other state parameters or properties, the substance properties, only can be defined by the nature of that substance. So we are going to do the same way, looking onto another properties of substance or state properties of internal energy U. So to do so, we will relate the energy equation, which constitutes of one of the state parameters and also the state equation. Issues that relate to the PVRT, because the internal energy we cannot actually observe it, so this is describe the state energy of the system, but a PVRT is a physical state. Okay, so to put it, to see the relation of this, because we're dealing here, so we can have only three properties at a time to make use of this differential equation, whereby when what we have done previously that the change of volume, say from 1 to 4. Let's say the change of volume from 1 to 3. So the change of volume from 1 to 3 through 1 to 3 process is equivalent the change of volume due to the change of temperature. So you see that from 1 to 2 is due to the change of temperature, the temperature change, but the pressure is constant. So from that we can have the rate of volume change due to the change of temperature at the temperature near to change of temperature near to 0 at constant pressure. So we just multiply how much the change of temperature, plus when we go to 2 to 3, the temperature is constant through this process 2 to 3, but the pressure is changing. So again we will obtain the change of volume due to the change of pressure at constant temperature, multiplied by the change of pressure. So we're going to make use of this. So but we try to we change, instead of V here or P or T, to an internal energy or any part of the energy equation with what we can have. Okay. So what kind of combination we could have relating the energy equation with the state equation? So we can have a pair of T and V. So U energy with T and V, T and P, P and V. So first we try to look on U, T and V. So just using the same concept, and then we are going to observe the change of U, change of internal energy due to the change of temperature at constant volume, and the change of temperature, the change of internal energy due to the change of volume at a constant temperature times the change of volume. So this is just an expression just to make a relation such way that there be a change of an equation, an energy equation coupled with the state equation, such way that how the internal energy change due to temperature and volume. So we need to make use of both energy equation and the state equation later on. So we try to, because we are looking into the internal energy, then we can make use of the in the first law equation or the energy equation, whereby the change of internal energy is also equivalent to the change of the amount of heat interaction between the system and the surrounding minus the work done. So PdV, so I just put it directly. So this and this, because again we internal energy can hardly be observed, so we cannot actually measure the amount of directly measure the amount of internal energy change. So what we can do is we can make use of this, just putting this equation into this energy equation. What we get, make the heat interaction as a main component, just to make things easier for this analysis, and everything here put it inside, which give T, V, V, so minus that one, or not minus because we already changed, put it this way, so it should be plus P dV. Okay. Take note, all of this value is a specific value. So just to make it more simpler, so I can factorize the value dV, so this is plus dV. So this another expression of energy equation which already include a state properties within the energy equation. Okay, so what we can make use of this equation, then we can take a look of how does this equation describe a few processes. So what kind of process, thermodynamic process we already go through is we have isothermal process, which is del T equal to 0. We have the isobaric process, whereby del P equal to 0. We have an isochoric process, whereby del V equal to 0, and then the last one we have an adiabatic process, whereby del Q equal to 0. So we will go one by one to look what kind of value we can obtain from here. Okay, so if we try to look first on the isochoric process, whereby the amount of heat, change of temperature, and all of these will be at a constant volume. So whenever we look upon the constant volume, this del V will give us to 0 values. I'll just make this one copy because I need to do it few times. Okay, so this one will become for del V equal to 0, so this becomes 0, which reduce the equation into del Q at constant volume V del T at constant volume. And then if you look at this expression, is amount of heat interact with the system and how much the temperature change of the system temperature change. So this proportion we already established before, in such way that the dq is really proportional to the change of temperature, and then we already obtain that because this is a specific values, and so this one will be equal to Cv dt. So if we compare this equation and this equation, so this is a constant volume. So if we compare this and this, and then we can conclude that actually this change of internal energy at constant volume is actually equal to Cv. For case where del P equal to 0, so this is what we get previously. So we can make use this equation. The conclusion we get obtained from here, we can replace with this rate values. So this is a constant, so I can just replace these values with the value that that we're familiar with, which is CV. This is also specific values, CV. So at del P equal to 0, so this will be at constant pressure, and constant pressure. And then if we look upon all this this relation, this del Q relation especially, we can do the same comparison with this, such way that whenever the del Q at constant pressure is also equivalent to Cp dt at constant pressure. So everything around is at constant pressure. And if I were to put and then directly replace this value, so again we will get that Cp dTp minus Cv, let's put it this one together, dTp equivalent to this W del V plus P dVP. Okay, so this del Tp I can just differentiate all of this equation with the change of temperature at constant pressure. Then we will end up with Cp minus Cv is equivalent to the del T at constant pressure. Okay, so when we look onto this method, then we already know this relation, and then we know about this, then because we can just derive this relation with the ideal gas law. So if I were to differentiate an ideal gas law, which is PV equal to RT with d dt, then I will directly this one at constant pressure. So what I will get is del V del T at constant pressure, so which is equivalent to this, and the other side will equivalent to R. So what about this? So we don't have these values. So what are actually these values? So what we can make use the identity we already established before in such a way that dx dy as constant z, dy dz at constant x, and another one dz dx at constant y equal to -1. So if I were to include this del u del v at constant t, so this del v del t constant u, another one is del t del u at constant v equal to -1. So we try to look upon what is del u, so I put it everything on the other side. T, which is equivalent to del u del t at constant volume, del v del t, this one is del t del v at constant internal energy. Okay, so so this value we already established before. Equivalent so I could reduce this value into Cv del T del V at constant internal energy. So if you remember that for an isothermal the change of U is equivalent to Q minus W. For isothermal process, there will be no change in internal energy, which is referring to the constant internal energy. But this work done is done by the system, so there will be a change of Q. Okay, there's an interaction of Q. So if we're dealing with a condition where we put a system going through a free expansion, there's a initial volume, initial gas here filled with gas, another one is vacuum. So this one is being dipped into water. So by isothermal process, whenever a system expand, not free expansion, expand to isothermal process, there will be a amount of heat flow from the outside to the inside. Okay. So if we are dealing with this kind of expansion, there's actually no work done, because this is a free expansion. As soon as this membrane or valve, this membrane has been removed, the gas will quickly expand, but there's no work done here. So there's no work done. Then if there's no work done, if there's a heat flow, then there will be no change of internal energy as well. So because there shouldn't be change of internal energy here, so we try to look whether there's a change in temperature or not from these cases. Okay, so no work done, the internal energy should be constant, so there also will be no Q flow. So if there's a Q flow, there's a significant change in temperature, then this relation will not be equal to 0. So when this experiment known as, there's a temperature thermometer here to measure there's a temperature, because if there's a certain amount of heat absorbed here, so the heat is absorbed due to a slight change of temperature, so they will not be equal to 0. The slight change of temperature, then there will be a heat flow through here to the system, which then we will observe some temperature decrease from this external liquid. So this is what we call a Gay-Lussac-Joule experiment. So from this experiment, they obtained that there is no change in temperature, thus conclude that the value for del T del V constant energy equal to 0. But for ideal cases only, it's actually equal to eta, which is a Joule constant. So for non-ideal cases, there will be a certain significant values. So for an ideal condition, this value equal to 0, thus give this value equal to 0, then CV is not equal to 0, then this have to be equal to 0. Value del V constant T have to be equal to 0, which when we obtain that del U del V is equal to 0, equation can be reduced. So this one equal to 0, as this equal to P del V del T, and this one we already established just now is actually equal to R. PV change of volume equal to 0, we obtain that del U del T at constant V equal to CV, and then with that we get this another form of energy equation. Sorry, this is not Cp, it should be Cv. And at dP, at change of pressure equal to 0 as an isobaric process, we could further this equation into this kind of equation, and then we able to reduce this part of the equation, which leads us to a much more common equation where Cp minus Cv equal to ideal gas constant, with the help of J. Luzak Thomson J. Luzak Joule experiment, where they find that for an ideal gas condition this value equal to 0, but if not, then we go equal to the Joule coefficient. Okay, so at constant temperature, so what we get is constant temperature with delta equal to 0, so this will be our general equation. At delta equal to 0, so which means that it's at constant temperature, everything at constant temperature, so this will become 0 at constant temperature. And what we can obtain from dq, we could do the same thing, but just bear with me for this. At constant temperature we can have a Ct as well, Ct, which means the specific heat at constant temperature, and dT. So since that is at constant temperature, then we don't have this change of temperature will become 0, then Ct will not be equal to 0 because dq is not equal to 0. At isothermal process, there's a q dq, there's a net heat exchange with the system and the surrounding. So dt equal to 0 because we are dealing with the constant temperature here. Then that leads us to the Ct to a value of infinity, very high, positive or negative value. Okay, so this does not help us anything, but we could reduce this equation further such way at constant temperature. So dq will equivalent the last part is at dq for isobaric process, dq equal to 0. So from here, from this equation, we will get this equal to 0. So what we obtain from there is Cv within entropy is Q over T. So when this Q equal to 0, it's a constant entropy, which is S, that we will discuss in further details. So this will be del T del V at constant entropy equal to negative of T plus P. So that's thing. We will discuss this later on.